Okay, fine. So, good afternoon to all. I'm Mr. Kumbhare, lecturer in electronics engineering at Government Polytechnic India. Today's topic for presentation is simplification of logic circuit. So, basically, we will continue with the topic which we covered in last, what we can say, lecture. So, the content for today's presentation are canonical SOP from Miss SOP form from truth table, then its gate level implementation, how we can do, and its simplification. Similarly, we will see the POS form and then its gate level implementation and then simplification. So this thing we had already seen in previous lecture. Once again, we'll go through. Okay. So suppose we have a truth table of any circuit and it is asked to form, draw the or write the sum of product form of that circuit. How to do that? So what you have to do, you have to consider rows, okay, of truth table which are having output is equal to 1. This is the one thing which you have to think of. Then for each such rows you have to form the minterms. Okay, you have to form the minterms. We have already seen this, what is minterm and what is maximum. So for input variable 0, you have to mention that input variable as in complemented form, and for input variable 1, you have to mention it as uncomplemented form. And then you have to sum all such minterms to get the canonical SOP. Let's see the example. So this example we had already covered in previous lecture also. So basically this truth table is for full adder. Now here we are having two inputs A and B. C is nothing but carry input. So if we add these three, we are going to get these sums and this C out. C out is nothing but carry out. Like you have already done addition in mathematics. So there you know that if you to add two things, there can be one thing that some carry will be there initially and carry may be generated from that. Suppose for example, I'm adding 1, 8 and then let us say 8, 5. So if I add this, what I will get, 8 plus 5, 13. So 3 will be there and carry will be generated. Now you can see this is 1A, this is B and this is carry input. Now if I add this 8 plus 1 plus 1, that is 10, so 0, and there will be a carry out which is nothing but this one. So this is carry out, this is carry input. So in addition of two numbers, we can have carry input from the previous output and carry out from the current output. So in the similar way, this is our carry input which we have to add into the given numbers like this. Here the numbers are 1 and 8, but the carry input is 1, so we are adding 3. Okay, similar way we can have 3 different addition numbers to be added, and that will give us sum as well as carry out. So if we do so this truth table we have seen in previous lecture. So 0 plus 0 plus 0 is 0, there will be no carry out. 0 plus 0 plus 1 is 1, carry will be 0. 0 plus 1 plus 0 is 1, carry will be 0. 0 plus 1 plus 1 is 0 and there will be a carry. 1 plus 0 plus 0 is 1 and there will be no carry. 1 plus 0 plus 1 is 0, there will be a carry. 1 plus 1 is 0, so 0 and no carry, there will be a carry. 1 plus 1 is 0 plus 1 is 1 and there will be carry. So like this. Now it is we have to, okay, this is a truth table, but if you want to implement it in hardware, you have to form its equation. Now how to form the equation? So you can form equation in two forms. One is either SOP, that is sum of product, or product of sum, POS form. So here we are seeing sum of product. So you have what we said in previous slide. You have to consider rows or truth table which has output is 1. So if I want to write down equation for sum, then I have to consider those rows which are having output equals to 1. So I have to consider these rows. Okay, this and this. These rows I have to consider. Now for these rows, I have to find out the minterms. Okay, for such rows, I have to find the minterms. So for this, the minterm will be since A is 0, if input variable is 0, here input variable is A. So if it is 0, you have to mention it in complemented form, that is A bar. So that's why A bar. Then B is 0, again B bar. C is 1, so uncomplemented form is C. So A bar, B bar, C. A bar, B bar, C. Similar way, you have to find the minterms for all these 4 rows, and then you have to add all these 4. So if you observe, we'll get minterms like this: A bar, B bar, C for this. For this, A bar, B, C bar, A bar, B, C bar, plus A, B bar, C bar, A, B bar, C bar, plus A, B, C, A, B, C. So like this, we can get the equation for sum. In the similar fashion, we can get the equation for C out, that is carry out. So here we have to find out 1 in the output. So 1 is here, 1 is here, 1 is here, and 1 is here, right? So if you now we need to write the C out equation with the help of these 4 rules. Okay, and you can write down their midterms. So here we have A bar, B, C, A bar, B, C. Okay, this. Then here A, B bar, C, A, B bar, C. This. Then A, B, C bar, A, B, C bar, and A, B, C. So A, B, C, like this. 4, and then you have to add it. So these 2 equations we can get from the truth table. Now, since we got the equations in sum of product form, we can implement it in hardware. How to implement it? Let's see. So from this previous slide, I am taking out the equations on the next slide. So sum is A bar, B bar, C plus A bar, B, C bar plus A, B bar, C bar plus A, B, C. Now we need to implement it hardware. How to implement it? All of us know that A bar can be represented with the help of NOT gate. And whenever we are having A bar, B bar, C bar, means such type of product terms that can be represented with the help of AND gate. And some will be represented with the help of OR gate. Let's see one by one. So I want A bar. So what I can do, I can have 3 inputs, A, B, and C. If you are not understanding, please interrupt me in between so that I will tell you one second. So we can have 3 inputs, A, B, and C. So we have 3 inputs. Now I want A bar. So what I can do, I can apply it to NOT gate. That will give me A bar. Similarly, I want B bar. So I can apply NOT gate, and that will give me B bar. C is as it is, so C will be carried forward. Now I want product of all these 3, A bar, B bar, and C. So what I need a AND gate. So I'll connect AND gate over here, and that will give me A bar, B bar, C. In the same fashion, we can find out A bar, B, C bar, A, B bar, C bar, and A, B, C. So this A bar, B bar, C bar can be found like this. I want A bar, so A will be applied to NOT gate. That will give me A bar. B will be as it is, and C will be again applied to NOT gate, so that will give me C bar. So that will give me the A bar, B, C bar. In the similar fashion, I can have A, B bar, C bar, and A, B, C. Wait, something is not correct. So here the correction is there. This should be as it is because I want A, B, C. Let me correct this. Give me a minute. So there's a correction over here. So this line should be direct, okay, and there will not be NOT gate. There will be no NOT gate. Like this. So this will be only B. This will not be there. This will not be there. So only B will come, C will come. So A, B, C. And now we need to add all these 4 terms. So I need OR gate. Okay, so that will add all the inputs, and that will give you the sum. So like this, we can complete this sum equation. So now here we have implemented this. So this is called as hardware implementation or gate level implementation of the circuit. Now if you observe, we have how many gates we require? 1, 2, 3, 4, and 5 gates we got required. Out of this, 4 will be 3 input AND gate, and 1 will be 4 input OR gate. Okay. Now, the same circuit, this implementation can also be realized using AND implementation. Okay, so instead, NAND implementation, NAND realization. So the same circuit can be realized with the help of NAND. Now, how to do it? Let me show you one example, and then we will convert this into NAND. So let me present you another screen. So stop sharing. I'll share another screen. Is screen visible? Is this screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Sir, visible.
Sir.
Okay, fine. So what we are doing here, we have this equation: y is equals to ab plus ac bar plus bc. Okay, this is again sum of product form. Now, if I want to realize it, how I can realize? I can realize it in two forms. One is AND OR implementation, like we had done for our circuit like this. Okay, or I can implement this circuit in NAND realization. Now, how to convert this AND OR representation in NAND? It's simple. The equation is AB plus AC bar plus BC. So what I can do, I can take a note of that. Okay, means Y bar. Okay, the initial equation was AB plus AC bar plus BC. So I'm taking note of both. As soon as I take note of both, what will happen? What will happen? We can apply De Morgan's theorem on this equation. Okay, we can apply De Morgan's law on this. So as soon as I apply De Morgan's law, what we will get? AB whole bar dot, because plus will be converted into dot, AC bar whole bar dot BC bar. Now if you observe, this AB bar is a NAND, means equation for NAND. Okay, so this can be represented with y1, this can be represented with y2, and this can be represented with y3. So where y1 is AB bar, y2 is AC bar whole bar, y3 is BC bar. Now if you observe, this is nothing but your NAND gate equation, because NAND gate is nothing but not of AND gate, and AND gate is AB, and NAND gate will be AB bar. So we can realize this with NAND gate. That's why what they had done, AB bar. So this is y1. Similarly, AC bar whole bar. This is y2. Similarly, BC bar. So this will be y3. And now this all will be applied to another NAND gate, and that will give me the output equation. So in general, if I would like to tell you, the OR and OR implementation like this can be converted into NAND implementation. How? Simply by replacing AND gate with the NAND gate and OR gate with also a NAND gate. So this can be implemented with the NAND gates. Okay, so if we want to convert this AND OR implementation of our sum of input, how we can do that? Just you have to connect, okay, like this. Okay, there is a correction over here again. Should be direct connection. Okay, and this also should be direct connection. Typing mistake is there. Okay, B bar will not be there, and C bar will also not be there. This will be B, this will be C. So if you observe, this circuit and OR implementation is converted into NAND implementation directly by replacing AND gates with NAND gate and OR gate with NAND gate. Got it? So like this, we can convert even AND OR implementation with NAND implementation. So the sum of full adder can be realized or implemented with the help of AND or gate or NAND gates. So these two types of implementation can be possible. Okay. So if we implement this and if we apply input to the circuit, that will give me the sum of full adder. Now, the problem lies with this type of connection is that how many gates required? 5 and OR gate, means 4 and 1 OR gate, or 5 NAND gate I need for implementation of sum. But so this makes the circuit bigger. Now how to reduce the circuit? The circuit can be reduced by simplifying the equations. So what we can do, we can simplify this obtained equation A bar B bar C plus AB bar C bar plus AB bar C bar and plus ABC. If we reduce this expression or simplify this expression, then we can get the reduced form of implementation, hardware implementation. Okay, so how we can reduce it? We can club this AB bar C and this ABC and this A bar BC and this A bar C. So like this. Okay, so I brought this near to this. Okay, so what I get, A bar B bar C plus ABC plus A bar B C bar plus A bar C bar. Now I took C common from this to this and I got C A bar B bar plus AB. I took C bar common from this and this is C bar A bar B plus AB bar. Now we know that XOR, okay, if I have A and if I want to take XOR of it with B, that can be represented like A B bar plus A bar B. This is XOR. So it means that A not B plus A B not or bar is nothing but XOR. So this is A XOR B. Okay. So what I can say, this is A XOR B. A XOR B not. It should be this. Let me write it clearly. Let me take another ink. So I can write down like this: A XOR B. Okay, and this is in bracket. This is our C bar. Now A bar B bar plus AB. This is NOR gate. Okay, sorry. This is XNOR gate. So this A bar B bar plus AB also can be written like this: A. If I take A bar, sorry, or if I take the this not of this. Okay, what will happen? Let's check out. A bar B plus A B bar. If I have this, okay, this XOR, and if I take not of this, what I will get? Let's see. So since this is whole not, I can use De Morgan's theorem. So what I will get? A bar B bar dot A B bar whole bar. Again we can apply what we can say, De Morgan's theorem to this as well as De Morgan's theorem to this. What I will get? A bar whole bar plus B bar. It's difficult to write using laptop. Let me once again try. So the De Morgan's theorem can be applied to this. So what I will get? A bar whole bar B, sorry, plus, this is plus, okay, just excuse me, and then B bar, and this is bracket, okay. Similarly, I can write down for A B bar whole bar. I can apply De Morgan's theorem. So what I will get, A bar plus B bar whole bar, like this I can mention. Now if I simplify this, A bar whole bar is nothing but A, okay. It is similar to A plus, this is B bar, and this is A bar plus B bar. Am I audible to all of you?
Yes,
Okay.
sir.
Now if you multiply or if you simplify this, what you will get, this A into A bar is how much? 0. A into A bar is 0 or not? A dot A bar plus this A into B, A B plus this A bar and B bar. I can write down this like A bar, B bar plus B into B bar. So B into B bar. As we are already aware about Boolean's theorem, we know that A bar dot A is nothing but 0, B bar dot B is nothing but 0. So I can write this equation as AB AB plus A bar dot B bar. So it means that this A bar B bar plus AB is nothing but A bar B plus AB bar whole bar, right? So I can replace this with this. So it is similar to C into A XOR B whole bar. Okay. Now if you observe, this is again C. Let us assume this is Y. A XOR B is Y. Means I can replace this like this. So let me change the ink. So I can write down this equation like this. C, I'm assuming A XOR B is Y. So Y whole bar plus C bar Y. Now if you observe, this is nothing but again another XOR, which is C XOR Y. So I can write down the whole equation as A XOR B, because okay, this I can write down like C XOR Y. Now if I replace Y with A XOR B, what I will get? C XOR A XOR B. So that's why A XOR B XOR C. Now this can be implemented like this, A XOR B, and so this becomes Y XOR C. So that will give me sum. Now if you observe, only 2 gates are required, that is 2 XOR gate to implement A XOR B XOR C, or sum of full adder. Or we can say we need 3 input XOR gate, 3 input XOR gate to implement the sum of full adder. So simplification of SOP in this fashion will reduce the size of circuit. Okay, it will reduce the size of circuit, because here if you observe, we required 4 AND gate and 1 OR gate for implementation before simplification, or we needed 5 NAND gate for implementation before simplification, And as soon as we simplify the given expression in sum of product, it will require only two input XOR gate or one three input XOR gate. So that is the benefit of simplification of sum of product, that it will reduce the size of circuit, and obviously it will reduce the cost of circuit. Okay, all of you got this?
Yes, sir.
Fine. Next is gate level implementation of Cout. So I'll just directly go to the main circuit. So this is the circuit. I want A bar BC. So A is applied to NOT gate, that will give me A bar. Then A bar BC will be applied to AND gate, that will give me A bar BC. In the similar fashion, I'll get a remaining 3. And if I apply all these 4 to the OR gate, that will give me Cout. Again, this implementation can be converted into, this is AND OR implementation, which can be realized using NAND gate. Just we have to replace AND gate and OR gate with the NAND gate, and that will give me NAND realization of the Cout of full adder. Now, if we simplify this, what will happen? Okay, now again, we need 4 AND gate and 1 OR gate for implementation of Cout of full adder, or 5 NAND gate for implementation of Cout. So how to reduce the circuitry? So by simplification we can do that. So this is the equation given in simplification, given in the Cout of full adder. So what we can do, we can ABC can be mentioned 3 times, as we know that A plus A is nothing but A. Similar way, ABC plus ABC plus ABC is nothing but ABC. But for simplification purpose, I have splitted it into 3 ABC. After that, I will club this A bar BC with this A bar ABC. Then this AB bar C with this ABC, and let us say this ABC bar with this ABC. Okay, I will club this. So if I club this A bar BC, ABC, AB bar C, ABC, ABC bar, ABC. Okay. Now if I club this within these two, I will get BC common, and A bar plus A, we know that it is 1. From this we will get AC common, and B bar plus B will be 1. Then from this will get AB common, so C bar plus C. So this is the reduced equation for Cout. Now if I want to implement, that can be implemented like this. I'll get 2 input AND gate, that will give me AB. So here I will get A, B, okay. Then 2 input AND gate, this will give me BC over here, and this will give me AC. Now I need to add it, so I will have 3 input OR gate, and that will give me Cout. Now what is the another benefit? The another benefit over here, I need only 3 AND gate and 1 OR gate. So we have reduced 1 AND gate from the previous circuit this. But the major benefit we got, or major benefit we achieved in this circuit is, since we are using only 2 input AND gate, which is much simple than 3 input AND gate. Okay. Also, we are using 3 input OR gate, which is much simpler than this 4 input OR gate. So simplicity of this circuitry and cost of this circuitry will be very less compared to the previous circuit. That's why simplification of sum of product terms is required, and that to be done. For what purpose? Number one is to reduce the size of circuit. Number 2 is to reduce the cost of circuit. And number 3, to simplify the circuit. Because time required to process the inputs for 3 input AND gate is much more than 2 input AND gate. So this will increase the speed of circuit, because the number of inputs are less, so obviously the processing speed will be much faster. So in this realization, you will get output much faster than this implementation. So this is also one of the thing. What are the four things I said? One is to reduce the size of whole circuit. Okay. Number two, to reduce the complexity of the circuit. Okay. To reduce complexity of the circuit. Number three, to reduce the cost of overall circuit. Okay. To reduce cost of circuit. All these three will be reduced. Okay. Reduced. And the fourth advantage is to increase speed of circuit. Increase. Fourth point is speed of circuit. So the speed of this circuitry will also reduce. That's why simplification of SOP or POS form is required. These are the advantage of simplification. Okay, I hope all of you got this. Please reply.
Yes, sir.
Okay, fine. Next is canonical POS form from the truth table. Previously, what we did, we used what we used out means rows which were having output equals to 1. For POS, we have to use the rows which are having output equals to 0. So inverse of previous one, and we have to form the max term. For max terms, the input variable with 1 will be represented in complemented form, and input variable with 0 will be represented in uncomplemented form. Okay, and then you have to multiply all those to get the canonical SOP. So this is the way. So previously we used rows with output 1. Now we have to use rows with output 0. So this one, this one, this one, and this one. So if we take this, we have to consider this row. Okay. So we have to, if A is 0, we have to consider A. So A plus B plus C. Okay. Into here 0, so A is 0, that's why A, plus B is 1, so B bar, plus C is 1, so C bar. So it is just a reverse of previous one. In the similar fashion, we have to take this and you have to take this, and that will give you the expression like this for sum. Similarly, you can go for C out. So for C out, you have to take the rows which are having output equals to 0, this 4, and then you have to consider their input, this one, this one, this one also, and then this one. Okay, so if you took this, what you will get, A plus B plus C, A plus B plus C bar, A plus B bar plus C, and then A bar plus B plus C. So like this you will get C out. Now how to implement this? So I have taken it on the next slide. So this is the equation. This can be the implementation. I want A plus B plus C, means OR gate I will apply. So ABC will be applied to OR gate, and that will give me ABC, A plus B plus C. Similarly, I want A plus B bar plus C bar. So A, B will be taken applied to NOT gate to get B bar. C will be applied to NOT gate to get C bar. So A plus B bar plus C bar, and in the similar fashion I will get all the 4, and then we want to take a product of all this, so that will be applied to AND gate. So this is a 4 input AND gate, and these are all 3 input OR gate. Now this OR and this is also called as OR AND implementation. This is also known as OR AND implementation. Previously it was AND OR, now this is OR AND. So in POS we have OR AND implementation, in SOP we have AND OR implementation. Okay, So this or and implementation can be converted into nor implementation. Just you have to remember the first one. Okay, since this is or, it will be represented nor. Previous one was and or, so and NAND. It's just like that. Now if I want to implement it in nor implementation, just we have to replace this or with nor and this and with nor. So this will be like this. This is a NOR gate. So nor. Just we have replaced the given implementation in this way. So that will give me the C out. So this is nothing. Sorry, this is nothing but your sum. This is your sum. This is your sum. Okay. So I hope all of you got this. In the similar fashion, we can we can simplify this POS form, but simplification of POS form is bit complex, because this cannot be directly simplified. So what you have to do, you have to first simplify this by multiplying each of the term, and then you have to get the sum of product. Okay, so A will be multiplied with A, then A will be multiplied with B bar, then C bar, and so on. Like this you have to do, and you have to get the SOP first, and then you have to again simplify it, and then you have to convert it into POS form. How to convert SOP to POS, that we had already seen in previous lecture. So this becomes complex in simplifying POS. So that's why we will not prefer this. In the same fashion, cout can be implemented in gate level logic, and then, but for simplification point of view, it again you have to convert this POS form into SOP form. You have to reduce it, and then you have to get the POS form. So that is the and this makes this difficult to reduce the POS. All of you got this? Any doubt? No
Yes,
doubts?
sir. No, sir.
Okay,
No, sir.
fine. So the simplification of POS and SOP form is bit complex in this way. Means just now we have seen that how it is complex. Let's take this example. Okay, here what we had to do, we had converted this ABC into this, and then we have plugged, and then we did all this stuff, right? So this is okay, but this is complex, so we need a much simpler process. So we have one more much simpler process, and that is known as K-map technique, which is the second simplification method. Right now I will give you the brief about K-map technique. From in next lecture we'll have the this bigger in depth description about K-map. So do you have any questions or queries on this POS and SOP simplification? Otherwise we'll go to the K-map. Any queries or questions? No queries? Any doubt?
Can you explain one time NOR
NOR
gate?
gate. This one?
How?
This one? Okay.
Yes, sir. Yes,
Let
sir.
me show you another screen here. So what happened? I had POS form like A plus B plus into A plus C into B plus C bar. That can be represented like this. And this is similar to our this implementation, right? This one and this one is similar, correct?
Yes, sir.
So now if I want to convert this OR and implementation in NOR, how to do that? That can be done like this, that I had previously, okay, don't consider this bar and this bar. I had previous expression like A plus B into A plus C into B plus C bar. And I wanted to convert it into NOR implementation. How to do that? We have to take the bar or complement of Y. So if I take that complement, then we can apply De Morgan's theorem to this. We know the De Morgan's theorem, and we can implement it. How? A plus B whole bar and dot will be converted to plus. this bar, whole bar is separating. Okay, it is separating to each term, and dot will be replaced with plus. Okay, so a plus b, this bar will come separately, dot will be converted into plus. A plus c whole bar, dot will be converted into plus. B plus c whole bar, sorry, bar whole bar. Now all of you are aware of the NOR expression. NOR is nothing but not of OR. Okay, so a plus b bar, this is the expression for NOR. So that's why I can replace it with y bar, y a bar. Okay, so y is a plus b whole bar, yb is a plus c whole bar, and yc is b plus c whole bar. So this can be represented with NOR gate. So that's why I can directly write down a plus this NOR gate over here. So that will give me ya, means a plus b whole bar, and this will give me yb, this will give me yc. Now if I give it to the NOR gate, another NOR gate, that will give me the y, because since there is another bar, okay, this will be added and another bar is there, so that will give me this expression a plus b into a plus c into b plus c bar. So what has happened here is that just you have to replace OR gates and AND gate with the NOR gate, and that will convert your OR AND implementation to NOR implementation. So we had used that same logic. We don't have to go for any calculations or mathematical simplification. Just what you have to remember is that this thing you have to implement it into OR AND logic, and after that just replace these OR gates, all OR gates, AND gate with the NOR gate. So remaining circuitry will remain as it is. Only thing is replacement of OR AND gate. So that gate will be replaced with NOR gate, and this AND gate is also replaced with NOR gate. So one thing I told you is that this is NOR POS. This is not SOP. This is POS. Okay. So one conclusion I told you is that in SOP, sum of product, we normally get equation realization in AND OR fashion. In which fashion? AND OR fashion. So this can be converted into NAND fashion. This can be converted into NAND fashion. So how to remember? SOP is AND OR. As all of you are aware, sum of product. So for product I need AND gate. For sum I need OR gate. So that's why it is AND OR realization. Since AND is there at first, so it can be represented with NAND. In the same way, if I want to implement POS, that is product of sum, POS sum. Okay, so for sum I need OR gate, and product of that I need AND gate. As OR is equivalent to sum, AND is equivalent to product. Okay, now this OR AND can be represented. OR is there first, so NOR. This can be represented with NOR. This basic conclusion we can draw. Okay, this basic conclusion we can draw. Just you have to remember this. If you have sum of product equation, then that can be represented with AND OR NAND. POS can be represented with OR AND or NOR. Suppose by chance in exam they have given you SOP form, and if they are asking you to represent it with NOR implementation, how you will do that? You have to first convert SOP into POS and then implement it into NOR. That will be much easier. Got this?
Yes,
so
sir.
this thing you have to keep in mind. This is the basic conclusion which we can draw. Okay. Is it okay now?
Yes, sir.
Fine. So another simple method, graphical method I would like to tell all of you, and that is, I will tell you that. Give a minute. Here, okay, here we don't have space. Let us see over here. Okay. So the next method is K-map. Next method is K-map, also known as Karnaugh map. Also known as Karnaugh map. K map or kernel. So in this K map, how to draw the K map? So normally K map is used for 3 to 6 variable simplification. Like here we have 3 variables A, B, and C. Suppose we have variables like from 3 to 6, then we can use it. Even for 2 you can use it, but it's better to go with normal simplification in 2 variables because that will be much easier. Now how to draw it? Suppose I have 3 variables. What I can do? I can draw a rectangle like this for 3 variables. Okay, like this. Let us say I have variables A, B, and C. I have variables A, B, and C. I want to use K map for this. So what I can say, I can write down A over here. A can have 2 values, 0 or 1. Okay, then I can split it, or okay, I can split it like this. So I can have B over here. Now in order to accommodate C, again I have to split it into 2 portions, 1 and so this will be C. Now I can write down its values like 0, 0, then 0, 1. Next, I cannot write down 1, 0. Instead, I have to write down 1, 1. Why it is so? Because I can change the bit only once. It means I can have only one bit change. So if I write down 1, 0, what will happen? This 0 will change to 1 and this 1 will change to 0. So 2 changes will happen, which is not expected. So that's why I am writing 1, 1. Now here only one change happened from 0 to 1. 1 remains as it is. And then I can write down 1, 0. All of you got this?
Yes, sir.
Okay, so this is 3 variable K map. Suppose if I want to draw for 2 variable K map, it is again easy. Just I have to draw a rectangle, square, which will have 2 variables like this. Let us say A and B, we have 2 variables. I can write down like this, A, B. So this is 0, this is 1, this is 0, this is 1. This is 2 variable K map. This is 3 variable K map. Got it? Yes or no?
Yes, sir.
I can draw this 3 variable K map like this also. Means instead of horizontal, do we need to draw horizontal only? No, we can draw vertically also like this. Like this also we can have the vertical K map. In this case, what will happen? This becomes AB and this becomes C. This is 0, this is 1, this is 0, 0, this is 0, 1, this is 1, 1, and this is 1, 0. Got it?
Yes, sir.
Okay, now suppose I want to draw for 4 variable K map. Then how to draw it? So what we'll do, we'll draw a square like this. This will give me 1 variable. Okay, this is 1, this is 1. This will give me 2 variables. This will give me 3 variables. So I need to draw the square like this. And then I can write A, B, C, D. And this becomes 0, 0. This is 0, 1. This is 1, 1. And this is 1, 0. In the same fashion, 0, 0, 0, 1, 1, 1, 1, 0. This is 4 variable K. All of you got this?
Yes, sir.
Yes, sir.
How to draw the K map?
Yes, sir.
Okay, 5 and 6 variable don't think about right now, because that is not in your curriculum. Just you have to think about this much. That's it. Now again, the thing is AB should be here or here. It doesn't matter. You can write down AB here. You can write down CD here. It doesn't matter. Fine.
Yes, sir.
Yes, sir.
Okay, so all of you got this? How to draw this 2, 3, 4 variable K-map? Got it?
Yes. Yes,
Okay,
sir.
fine. Now, what I will do, I will simplify the sum of uh, full adder. Just give me a minute. I will erase this because we have only 3 variables. I can use what? This 3 variable K-map. Now, I will show you the simplest way. Now, this is 3 variable K-map. This 3 variable K-map I can draw over here. This is A, this is BC. Okay, this is 0, 1, this is 0, 0, 0, 1, 1, 1, 1, 0. Now, what we need to do, we need to find out sum for, so equation for sum. So what I will take, and that is in SOP form. So what I will take, again, I will take the terms with 1. Here, A is 0, right? So A is 0, means it will lie in this row. Then B is 0, C is 1. B is 0 and C is 1, means this 0, 1, right? So I will write down in this row, in this column, 1. In the same fashion for this one, okay, for this one, A is 0, B is 1, C is 0. A is 0, B is 1, and C is 0, means this, okay? Then for this, A is 1, B is 0, C is 0. A is 1, okay, B is 0, C is 0, means this one. And then for this, A is 1, C is 1, B is 1. So A is 1, B is 1, C is 1. So now I can use this to write down this expression. So in this way, we can go for this sum. Got all of you got this?
Yes, sir.
Yes, sir.
Okay. So we can get the expression for this. Simplification, when such crisscross will occur, it means that this is the representation of XOR of A, B, and C. So I can directly write down A XOR B XOR C. Whenever such crisscross occurs, this represents this is XOR of A, B, and C. Now for C out, let's go for C out. So this is 1, okay, over here. So it has B is equal, A is equals to 0, B is equals to 1, C is equals to 1. So A is equals to 0, B is equals to 1, C is equals to 1. So I can write down this one. Next, this one we can take. So A1, B0, C1. A1, B0, C1 means this one. Next we can take this. So A1, B1, C0. A1, B1, C0, this. And next one, this we can take. So A1, B1, C1. A1, B1, C1, this one. Now we can reduce this. How to reduce? First of all, we have to look combinations. Okay. Here I have 1, 2, 3, 4, 5, 6, 7, 8. But I cannot do 8 cell combination because this, and this is blank, right?
Yes,
Yes
sir.
or no? So these are blank,
Yes.
so I cannot club it. Next, we have to see 4-bit combination. So can I do this? No, because these 3 are blank. Can I do this? No, because this is blank. Can I do this? No, this is blank. Can I do this and this? No, these are again blank. But so 4-bit combination is also not possible. Next, we go for 2-bit combination. So there are multiple combinations possible, and those are like this. I can have this combination, right?
Yes,
Yes,
sir.
sir. Sir. I can have this combination. 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 I can have this comb Next combination I can have, let me take another ink. Okay, I can have this combination, and I can have vertical combination, this one. Got it? So these three combinations I can have. Now I need to give the names for this combination. So for this combination, look,
A.
A is changing from 0 to 1. Since A is changing, we cannot take. Here B is remaining same in this combination as 1. C is also remaining same in this combination, so E is 1. So what I can say, B, C. Now for this blue color combination, okay? Now let us go for blue color combination, blue color. So in this blue color combination, A is 1. Is it changing? In this combination, A remains 1 over here, A remains 1 over here. So A is 1. So what I can say, A as it is. Now here B is changing from 0 to 1, right?
Yes,
So
sir.
B we cannot consider. C is not changing, so we can consider C. So that's why A is C. Then for this yellow combination, okay, in this A is again remain as it is,
1.
means 1. So that's why we can take A. In this B is remaining as it is, 1 1, but C is changing, so we cannot take C. So what we will take, only B. So and now you have to add this AB plus AC plus BC, AB plus AC plus BC. Now if you see the simplification of this, what you will observe, C out, AB plus AC plus BC. Got this?
Yes, sir.
So we have not done all these calculations just by placing what we can say, bits 1 1 1 1, and clubbing the bits, we can have the simplified version. So this C out can be written as AB plus AC plus BC. So without doing any simplification, just by graphical way, we can simplify the equation for C out or for anything. Got it?
Yes, sir.
So this is the way we can simplify it. Okay, for POS, how we can do it? Let's see it. Okay, for POS, let us say I want to reduce this. So how to do it? Again, this is 3 variable. So I'll draw a 3 variable K-map like this. This is A, this is BC, this is 0, this is 1, 0 0, 0 1, 1 0 1. This is 1 0. What you have to do in POS, we are considering 0, so you have to consider the rows which are having value 0, and those are nothing but this. From here you have to consider this one, then this one, then this one, and then this one. You have to consider this. So 0 0 0, 0 1 1, 1 0 1, 1 1 0. Can you note it down on
Yes,
page?
sir.
Just note it down,
Yes.
and you can tell me. Have you noted? 0 0
Yes.
0, 0 1 1, 1 0 1, 1 1 0. Have you noted it?
Yes, sir.
Okay, fine. Okay, tell me, what was the first combination?
0 0 0.
So I can write down 0 over here because I wanted in POS, right? So I will write down 0 over here. Next combination was
0 1 1.
So 0 1 1. So I will write down 0 over here. Next combination is
1 0 1.
1 0 1. So I can write down combination. Next is
1 1 0.
1 1 0 here. Okay, again this is crisscross, means with the help of what? XOR gate, right? With the help of
Yes,
XOR
sir.
gate we can implement it. So A XOR B XOR C, simply A B C. So like this we can simplify. Got it? So K-map helps us a lot for simplifying the equations and implementation purpose. So we'll see in detail in next lecture. Just a brief I wanted to give you. So that's what we cover. Okay, fine. So any queries?
No, sir.
Fine, then we'll stop over here. I think this topic is clear to all of you.
Yes, sir.
Okay, fine then. So in this week, upcoming week,